Good morning, everyone, and welcome to the JKMRC Friday morning seminar series. On behalf of the University of Queensland and the Sustainable Minerals Institute, I would like to acknowledge the traditional owners and custodians on the lands on which we meet today. We pay respect to their ancestors and their descendants who continue cultural and spiritual connections with country, and we recognize their valuable contributions to Australian and global society. And this for this webinar, it is my pleasure to welcome Dr. Edxon Licon. Edxon is a senior project manager at Setaqua and leads innovative research development innovation projects in decarbonization, biorefinery, and resource recovery. He holds a bachelor degree in chemical engineer, a master's in sustainable processes, and a PhD in chemical process engineer from the Polytechnic University of Catalonia. His expertise relates to advancing environmentally conscious practices and addressing key challenges in water management and resource utilization. He has collaborated in the development of innovative techniques applied to bioprocess, membrane science, and micro and nanofluidics. Today, he will present a seminar titled REECOVERY, Circular Economy to Produce Critical Raw Materials from Water in the Mining Industry. So let's give a warm welcome to Edxon, and thanks, Edxon. The floor is yours.
Thank you very much, Daniel, for your kind introduction. Well, actually, our today's seminar, it's I will try to explain a project that is being done in the south of Spain. Basically, it's a project that is related to an old open pit that has been not on operation during more than 20 years. And now, due to the economic and also the sociopolitical schemes nowadays in the global context, what was not in the moment economically feasible for several reasons, nowadays is very interesting. But we also wonder that this kind of projects is going to be really important for managing in all other sites, all over the world. And also in situations not only on reopening or remediation of all sites, but also for a sustainable closure or currently operating. And well, in the perspective of new regulation on discharge limits such as sulfates and metals, and also an increasing market dependence in critical raw materials, we think that a change of paradigm is important in the mining sector, and to create a more circular model is important in order to provide sources of currently available by primary resources. But in this particular case, in which we have water that has been in contact with metals for several years, and also iron sulfides that has been exposed to the atmosphere, well, we have a lot of contamination of sulfates, metals, and of course, in order to get into the old galleries, in order to reopen, create value from the resources that are beneath the earth, it's important to get rid of the water, but also take it as an opportunity in order to supply, in order to operate the old facilities and also neighboring areas with reusable water at the same time that we are producing value. This project is a 3-year project that we are 6 partners, which the coordinator is Mineral Australis, part of Grupo Mexico. Setaqua, that is a water technological center that is based in Spain. Acombiente, which is an engineering firm that is part of the Veolia Group, and some academic and research institutions such as the Universidad Politécnica de Catalunya, the Spanish Research Council, and an Institute of Non-Ferrous Materials from Poland. So basically, what we wanted to create an scheme of circular economy. We know that there is always some exploration money that needs to enter into the circle, and all these little arrows are wasted on opportunities, such as I mentioned. The EAT raw materials, as such, it's a huge network of more than 300 members. It contains also more than 600 startups, universities all over Europe, and basically it contains the whole entire raw materials value chain. And they are developing at several regional schemes, or how they call it, the REECE regions, important projects that are for several applications, such as is the case now, in order to have a more sustainable remediation and also outsource uh, new sources of raw materials, critical and there are also international strategic partnerships, such as in Africa, Americas, Asia, and so exactly the project objective of recovery is transforming those waters that I mentioned at the beginning in a novel source of materials. And in order to do that, we need to develop a resource recovery treatment train, which I will explain later, basically to demonstrate the ability to obtain metal sulfides from those waters, and at the same time try to recover rare earths in the form of oxalates by concentrating on a iron exchange technique, and to create value from that, at the same time that we're validating the quality of the standards of commercially available products in order to enter the value chain of all those specific products. And at the end of the day, to create a business model that can ensure the commercialization, the products, but also the technology. So how does the problem connect to the solution? So basically, we have a linear production in which polymetallic ore is introduced to an ore plant and some concentrates are produced. I was already mentioned in open pits where when they are not being operated, they are flooded, and this water, in this case specifically, they have kind of two open pits with about 10 hectometers of water that is contaminated and needs to be properly managed. So we are proposing the recovery route in which through three principal units, one for the recovery of metal sulfide, another for the recovery of oxalates, and then a final polishing part for water recovery reclamation, and also reduce at the same time to reduce the discharge. We are introducing a kind of a new concept in which we are also integrating a circular economy scheme with other sectors such as the chemical and agro-food sectors in order to have some raw materials in order to create some of the at the end of the day, I already mentioned we have a presentation to commercialize the new products of secondary sources, also to determine some indicators environmental will benefit value chains and also to have proximity in production in Europe, which is very important. And at the end of the day, also Acombiente, which is part of the Patagonia Group, we try to incorporate all the technology developed in their portfolio. So exactly, well, not exactly, but an overview of exactly the units that are recovery based. This first unit is a metal sulfide recovery unit that it bears three main components: a physicochemical pretreatment for the elimination of iron and aluminum and manganese, which could be problematic for several reasons related to the further units, but also in order to purify the products that we want to commercialize. So the combination of all these units that will be evaluated at TRL 7 at the beginning, and the idea is to come up with a technology readiness level of 9 at the end of the project by certification that we are going to have. And by using this project, we are going to design pilot plant that is going to be written at 5 kilometers per hour. Part of the water that is going to be produced during the precipitation of the metal sulfides. Once it is exhausted, it will pass through a series of ion exchange resins in order to separate high molecular weight and low molecular weight, and then crystallize them by an oxalic route, and at the end of the day to have a product that could be interesting for producing magnets. Then at the end of the treatment, there is another physicochemical treatment, a little bit more complex, that contains the removal of gypsum and at the same time calcium. Very important to protect the membranes in nanofiltration and reverse osmosis that will give us the opportunity to produce water fit for purpose, depending on which is going to be the end use of the water that is going to be covered. So we can have several sources of qualities that could be interesting for example, a very high quality for boilers or cooling stations, cooling systems, or other uses such as irrigation or water reclamation to work in cooperative environments such as in flotation stages with water that is considered soft but not as low conductivity or a reverse osmosis water. So basically, this is the general overview of what we want to do. There are some things to take into account from these units. From the environmental point of view, the first unit uses a circular model in order to produce the metal sulfides. We use a biochemical route in order to produce it. And we create a circular economy model, which we interrelate to other sectors, such as I already mentioned, to have principally glycerol from the production of biodiesel, which is a byproduct, and also a byproduct of petrochemical, such as the sulfur in base oil. So from the economic point of view, it will reduce the cost of the original sulfide. Currently, well, the most common and route to produce metal sulfide is just to use sodium sulfide, which is more expensive even than the sodium hydroxide, kind of very expensive chemical nowadays, which is in industrial application, at least here in Spain, and it's been avoided in an alkali form or alkali chemical in order to operate and modify pH. There are other processes such as lime that is more extensive acquired in the industrial sector, and such in this kind of configuration, we reduce a little bit the production cost also by introducing raw materials that contains also not footprint in the terms of CO2 emissions, because they are going to be considered natural and or biogenic. And at the end of the day, such as I will later, some of the emissions related to the production of the sulfide and sulfide will be captured by the same process. So the second unit is the oxalate. So from environmental point of view, we are introducing a secondary source, but it's difficult to find materials. There are not options in Europe for having this kind of sources inland. So it's very important to find alternatives in order to train or make more robust the value chain in Europe. From the economic point of view, there is the reduction of the price volatility related to things that happens outside the European borders. And also, well, there is some criticality reduction because the prices will be stable. We do not think that this specific project implemented at full scale will dramatically change the market in Europe. But what we think is that if several companies introduce the way of recovery, may have several percentage of the whole market. So I already mentioned the part of the water reclamation. So basically, it's reduce the water footprint, which is really important. And then from the economic point of view, there are going to be sources of needs also for remediation, not only the specific problems with contact waters or waters, but waters in general in the whole perspective of the mining operation. So this process is kind of complicated in a sense because there's a lot of units, but at the same time it has some robustness because it could be adapted and tailored to the final application. So the specific objectives, the highlights are that per cubic meter of water we aim to recover about 1 kilogram of metal sulfides, 70 grams of rare earth oxalates, and to have a 70% recovery of the water. And when implemented industrially, there is a capacity that we have been designing with the coordinator that probably the numbers are now. But of course, it's a project that is ongoing and we recommend the best key performance indicators in order to accurately well modify these numbers. So we have several work packages. We're going to pass very quickly just to show the structure. It's a quite a complex project that contains the go-to-market strategy where we need to determine the customer need, value proposition, the IP strategy, these kind of things, the project management, that is basically the coordination, project monitoring, the risk management, then the communication and dissemination activity, which this seminar is of course part of the strategy we're trying to follow in order to share with several audiences what we are working with. Education and training work package also working very closely with the university, with creating sources of people engaged to mining and also with high technology development. And the objective is to train early stage scientists, basically. There is, of course, a work package that already finished, and we'll show you some pictures of the design and construction of the site, which is really nice and we are very proud of. Then the operation, from integration and the circular economy strategy, as mentioned, quality standards that need to be defined. And at the end of the day, to determine the life cycle assessment and the life cycle cost of the whole process that we wanted to scale. So updates and results, which are really, really interesting and something that we are currently working with. Related to Work Package Zero, we are developing the way we are going to introduce the products into the market. And by products, I mean the minerals, but also the technology. There is an important value chain that is the rare earths that we are working with people from the north of Europe, refiners, in order to determine exactly the price of what we need to produce or to put on the market. We'll have once it reaches their door. So, and basically what I can say is that it's about the 60 to 70% of the current price of the concentrates that are available. And in the other point of view, there is the zinc sulfide, which is the primary component of the water that we can see nowadays in the current facility we are working with the project. So about the 40% of the mass of the dried product is zinc in the form of zinc sulfide, and it's really important this characteristic because it enters directly to what is considered a concentrate. So at the end of the day, we are aiming several facilities, but as of the point of view of the coordinator, they are going to introduce and blend the concentrate through the current process of producing concentrate. So very quickly again, let's review and then we can numbers and results. Establish a methodology for risk monitoring. So the project was very challenging. The construction of such a complex facility from nothing. The communication and dissemination, we have been attending several events. You are more than welcome to visit our website. It's recovery.eu, and you can see more information on the project. Contact us directly if you have some questions or you would like to share with us something that you were working in the last years. There is also the education and training. 2 doctoral students are working currently, a master student also. Through the university, we are engaged in current courses of master's and bachelor, developing workshops and open challenges to include in the course signatures. And it's really interesting to participate in these kind of things. So we develop all the flow diagrams, PNIDs, mass balances, laboratory scale experiments in order to construct when we have different kinds of side. And nowadays, currently, we are working with the optimization of it. We have created an integration with alternative carbon and sulfur sources to the process. And nowadays that we are reaching the end of the project, we are working extensively with the inventory for defining exactly what we want to measure and how to present the impact of the process in terms of sustainability indicators. And of course, the definition of the waste management is very important. Something that I didn't mention in the facility, they are reopening and the licensing they are acquiring is for the mediation of the site with operation within 30 years. And in the way that they are going to integrate this kind of processes is by refilling the galleries once they are exhausted in order to close completely in a more sustainable way once it reached the 30 years of the project. And then the project recovery is important because the waters is going to be in contact again with all the liabilities of the mining. And it's going to be important also to create this kind of process when closer again. So exactly how it looks like the recovery process. So get more into the deep. Well, we have a source of Nalcoya pit. We are obtaining about 3 to 5 cubic meters per hour from the pit. There is a first physicochemical treatment in which we are adding lime, peroxide, and flocculant in order to eliminate iron and aluminum. It's very important to mention that the water was considered anaerobic, and there is a segmentation of iron, which is in the form of iron 2, which is really difficult to eliminate only with pH 3. So we need to control the redox really well in order to be able to about the iron. Then the blowdown of the first chemical treatment into a crystallizer that interchange hydrogen sulfide that is produced by a bioreactor with is a USB reactor that is fitted with sulfur and glycerol, I already mentioned. Then the biogas that is produced or left passes through a scrubber that is part of the CO2. And after the remaining not usable sulfur, that is also convenient for us to have this kind of safety measurement, complicated gas, but from the explosive point of view, but also for the toxicity. Then there is also the concentration of the earth through the ion exchange alternatives. At the end of the day, you're analyzing by an oxalic form the earth. And then the blowdown of those processes are leading to the last physicochemical treatment membranes, in which we eliminate also by lime and flocculant the calcium sulfate, the important step of elimination of calcium carbonate. And we realized just a couple of minutes ago that the waters that I've been working with contains a little bit of magnesium more than the usual that you can find in water. So there, also that's something that we would like to open later for a different project. So working to try to recover also. What my progress with the filtration and reverse osmosis, basically the objective of this kind of units is eliminate hardness. The remaining sulfate, calcium, and magnesium is present after the physicochemical treatment tree, and then to eliminate conductivity by the reverse osmosis, and to produce a water that could be used to prepare chemicals in the facility itself, or also for irrigation. So how it looks like exactly. So this is just a top view of what we have. We have 4 different main areas. The area of physicochemical treatments. We will have a look into that. Then a region in which we have the bioprecipitation of metal sulfides, the area of recovery of rare earths by the columns and also the crystallizers, and then the polishing section of water with section and reverse osmosis. So this is how it looks like. These are the entrance tanks of the facility. You can see over there the physicochemicals, treatments, the preparation scheme for the line. The bioreactor is a huge one, almost 3 cubic meters, and we are producing about 1 cubic meter normalized of biogas every hour. And then the crystallizing unit, then there are over there some boxes. We will have a look later on what we already discussed about the exchange and the membranes. So a press filter just to recover what we have precipitating, and some ancillary equipment that is important for operating some hydrocyclones in order to see exactly the size of the particles we are going to work with in the flocculation or not flocculation or direct filtration is something that we are optimizing currently, and it's really important to have a look at that. So these are kind of sequential chemical treatments in which we add the shift of redox potential, the shift of pH by lime, and also the flocculant, and we have a flocculation chamber and some lamellas by separating the sludge from the clarified, and we are really happy with the results. Some problems, of course, of maintaining and driving the physicochemical treatment, but we are producing water. We just a couple of weeks ago we reached the 1,000 cubic meters treated in the plant, and we are really happy about just the bottles of the resins, the skids of membrane filtration, nanofiltration, and reverse osmosis. We know that this is the nanofiltration because we have this filter here, but I know it's complicated to determine. And then what about the results so far? So we examined exactly, we did an extensive characterization of the water that is present in the open pit. We determined an optimum pH in order to eliminate iron principally and part of the aluminum in order to not have problems and also contamination of the metal sulfides. We decided to work at about 4.5 after the first physicochemical treatment, and the results are really well consistent. It's besides the problems that we have been building up the bed of the separation of the sludge and the clarified. We do not have much problems with that, but it's a maintenance operation. Of course, it's a pilot plant and it's nice. And then talking about the bioreactor, we are really happy with the result. We have encountered also several problems with the stability of materials due to the complicated nature of the hydrogen sulfide, but we managed to work in redox conditions, which allow us to be sure that we are going to produce sulfide instead of methane, and also to have CO2 joining gas. So very stable process after the startup, and also the COD has been maintained during the last month, effectively less than 5 ppm of COD, of chemical time, and up to 2000 more or less when we have to again increase the concentration. Basically, we are introducing again the substrates, which are mentioned glycerol and sulfur in elemental form in the working problem. I hope you can see this graph. It was quite difficult in order to sum up the whole process in it. But basically, we have the characteristics and principal components that came from the pit, the pond. And then the first physicochemical treatment get rid of the iron and some of the aluminum. And the crystallizer eliminate all the aluminum, but also we have some thing that is present that also it's eliminated due to the crystallization. Then what enters into the exit of the ion exchange resins column contains almost indetectable traces of rare earths. And then in the end weight, we are producing, currently, we are trying to optimize nowadays the crystallization section of the oxalates. This is something that we are currently developing and we have not resolved yet. Hopefully, something about exactly the characteristics of the rare earths. So at the end of the day, then we have the elimination of sulfates, the lime, hardness, and at the end we have very good water that it's about 100 microsiemens per centimeter activity, which are really high quality water that could be mentioned in restricted processes such as boilers or cooling towers. So this is the images. Iron is present over here. Of course, this is the cake that we obtained from the press filters. We are trying to optimize exactly the structure, the general structure of the cake, because nowadays, as you can see, this is blotchy and not compact. There is a kind of a lot of humidity in it, and we need to work either with the pressure and also with a fluctuation pre-step in order to increase the size in order to have more pressure in this cake. And at the end, well, there's calcium sulfate that we producing at the end of the physicochemical treatment. Important thing to mention, we are as part of this kind of project specific, since we need to arrive to technology readiness level of commercial, we need to accurately see and oversee what is patentable and protected with IPR. We have constantly revising with some keywords what we are doing exactly in the process, and it allows us to identify some competition of some of the techniques that we are using, principally in the transfer of the hydrogen sulfide from the bioreactor to the crystallizer by a membrane contactor, and we have a patent request. Sorry for not strong results, but it's kind of difficult, this kind of thing when you are trying to define exactly where there is a patent that is not longer in working, but in order to determine exactly the novelty of the recovery process, so what we want to patent, we need to demonstrate that which is the difference of these kind of things. Well, it's been really very nice, the definition of what we wanted to show. So just we are coming to the end. I would like to use the few words just to tell us about my center. Is a research center based in Spain. We have 3 locations. The main one is in Barcelona, where I belong, but there is another 2 in Andalusia, Sevilla, another in Galicia, and one more in Chile. And also currently now there is just one that has been opened in Valencia community. So we are working closely with water operator. We are a water technology center, as you have seen through all my presentation. Water is the main conductor of the story that we want to know, and how to integrate the the circular economy philosophy in mining is very important from the water's perspective, and also to see a problem such as this kind of contact waters as an opportunity. So from my side, I think this is what I wanted to tell you. I would be really happy to answer your question and clear my contact details if there is no time for talking about a specific question that you may arise.
All right, thank you. Thank you very much, Edson. That's a very interesting presentation. I'd love to see all the technical challenges involved in this project. It's very good to see like this project coming up for improving the circular economy associated with the mining industry. So ask anyone that has some questions, send on the chat or raise your hand. I can give you allowed to talk. So I'll start like I have a few questions that's quite interesting. From developing this process, where was the most like technical challenges for improving like the recovery performance? Was it like on the more base metal side? Was in the rare earth elements? How was this process of developing this technology and see this processing workflow going? And why did you find like
Yes,
most challenging?
currently, I would say that the most challenging part is trying to create economical stability concentration of rare earths, because we are talking that the water is present in the open pit. It's about 20 ppms of the whole bunch of all the classes of rare earths. Of course, it's very important to concentrate them to this technique of selective ion exchange material, and then the weight would rise the concentration of orders of magnitude. And then having this perspective, we aiming that's why this 70 grams per cubic meter of rare earths to be recovered. But what we have been facing more problems, I would say, in operating conditions, I would say is the bioreactor. It's kind of challenging. So it's beauty in a sense in it, because you are self-producing a chemical that is expensive, such as the sulfide, in order to precipitate in a conventional metal sulfides. And you are outsourcing yourself, creating a network with other byproducts from several other sectors. But the operation itself is quite complicated due to the location of where it is. Sevilla is a place where the temperature varies a lot. You could have winters very with temperatures that become freezing, and then summer that you can reach 40 to 45 degrees. So it's quite complicated to stabilize a biological process in this kind of condition. I would say that those were the two main challenges, but in the other hand, in order to say something too good about the process, is that the robustness of the whole integration of the process through the physicochemical treatments and the membranes, you can ensure the quality of the outlets very precisely, with no variation in the consumable materials, in the energy requirements, and in the quality standards of producing. It gives you really important perspective of if it's going to be applicable in industrial scale or not.
Yeah, thanks. There is one question line, but I just want to continue a little bit. Like something like you say, like when you say, like for example, in this mine that you're dealing with is you have rare earth elements, but also rare earth elements you have light and heavy, and like the heavy has much more economic value. Which one do you have, for example, in this mine site? And like if, for example, you're dealing with some place where you can have more heavy rare earth elements, wouldn't that be more easily be to make like economically valuable, because the heavy rare earths a little bit like has more value?
Yes, actually, one of the things that we want to do with the process is, on one hand, classify them, so separate exactly the components, and to have mainly neodymium. This is the one we are trying to concentrate the
Yeah.
most, so we are trying to, to focus. But there is another bunch of light elements, light rare elements that also have their own market. And what
Yeah.
we have been talking with refiners is that if we get rid of cerium, which is a penalty in the concentrates, in the first column, we can increase the value of these light materials. So I would say that yes, as long as you have interesting concentration of neither uh, heavy or light elements, the process is going to be easy. So this is something that should be considered. Of course, the this recovery strategy, it is focused in waters that contains little amount, and that's why we are applying um, an exchange technology. But if the concentration is large enough, or the purification to go to another route, such as solvents or whatever, um, well, liquid extraction of this kind of things for purifying larger concentration, we could introduce this new unit in the whole system of recovery as well.
Right, thanks. I have more question, but like I will read first Juanjo. What type of social feedback have you received from the local community? Are they open to integrate the treated water into their agricultural activities?
Yeah, so well, this is a point that is characteristic from the site. The water that is going to be treated in the facility, it will not go to usages or to the environment. Most of the water is going to be used for the process and the operation of the plant, and the water is not going to be usable. It's going to be conducted to an emissary into a river. So, and it will have a kind of dilution effect. So basically, there is not going to be an option for usage directly. But the water that we are going to produce through the membrane processes would perfectly fit requirements for irrigation. So mainly nanofiltration, I think the waters that we are producing in terms of conductivity, in also the ratio of sodium versus calcium and issue could be also tailored in order when in not salinization of soil when using this kind of water. But in general terms, I would say the social perspective is more from the economic perspective of the reopening a site that historically was a source of employment, and it has more than 20 years ago closed. And now there is an opportunity for young generations to engage with mining activity, create value in their society. And this is the point of view that the whole facility, not only for the local community has on it.
All right, thanks. I will allow Graham to talk. If you wanna ask your question, Graham, can I mute your mic? No, that's Graham. Do you wanna unmute your mic to ask a question? No, it's working. Oh, let's see. All right. So for now, like the Graham's not replying, I have a question. So
Okay.
you developed this whole processing workflow based on this mine, right? And like this water and this kind of stuff. So how do you see, like, if you wanna like commercialize the technology in the sense, what would it imply, like changing, for example, a different mine, you're gonna have different type of elements happening. How much technical challenge that's gonna involve for change the type of mine, the water, like how are you gonna deal with this whole processing? Because I find like each water is going to be different depending on the mine that you're dealing with. So how do you see that?
Yes, basically one milestone that we see in the business plan in order to be applicable to several other facilities or scenarios, we need to accurately characterize the water and to downscale the process in order to determine exactly the operative conditions that will give answer towards the necessity of the end user. I can mention that there is another facility that is really interested, in which the main component of the metal sulfide is not zinc but copper, and it is very interesting from the simple point of view that is economically more interesting. So copper is more expensive than zinc, and uh, and of course the other kind of metals that are in the family, such as nickel and cobalt, are also really interesting. So we have not find, or we are not aware of sites in which the main component are others than zinc and copper, but we have seen that there are plenty of options on liabilities that if they are leached in the proper way, we can increase the content of rare earths, for example. We have been also looking into other facilities in which instead of the high amount of aluminum that is contained in this kind of work is iron, the main component. So there is also the possibility to produce a byproduct or a sludge that contains an important amount of iron that could enter towards their own value chain. So it's what how we see is that we need to get close with end user to evaluate from the characterization, lab scale perspective, the feasibility. And once we do this kind of study, we can accurately identify the OPEX and the CAPEX that is going to be needed in order to fully implement the whole funnel.
Oh, thanks. That's very interesting. I don't know if Graham, do you want to try to unmute? I don't know. Exactly. All right. I have more questions because I'm finding it very interesting. Could you go back to the slide where you show like the elements that you're doing going through the process and then you're extracting it? Yeah, there's one. So when I look at it, like for example, I see like the pond there has a few ppms of rare earth elements, and then through the process you kind of see the rare earth elements increasing and then decreasing after you do the extraction. What is this kind of pattern? What's happening there, like to make it increase and then?
Yeah, well, there are some addition of chemicals such as calcium, because we are using lime to make the pH shift, which of course modifies a little bit the content of hardness. But in general terms, what we're trying to do is just to conduct the rare earths towards the ion exchange, and then once it passes through, eliminate from the rejection stream the content of rare earths and concentrated inside the resins. And once you elute it, you can multiply by orders of magnitude its original concentration. So this is to say the root of the rare earths. But then is the zinc on one side, that this is the characteristic of the side I mentioned, that we wanted to eliminate it or to obtain it in the solid form in the crystallizer. So basically, we are trying to not precipitate a lot. You can see there is a little variation on some of with, with pH. That's why it was very important, as I mentioned, to accurately define the pH of the first physicochemical treatment in order to not alter too much the concentration of the product, like to obtain at the end of the crystallization and the ion exchange. And then the later units are basically just to reach a proper amount of sulfates content and also eliminate hardness and conductivity. So this is the strategy we are trying to follow.
All right, thanks. Very interesting. So Grant, he typed his question. So what are the rare earth elements bonded to in the water, in the wastewater?
So I can show you exactly what we have been. So basically the first column, what we wanted to eliminate or to concentrate, it's neodymium as a first, and also to eliminate cerium and lanthanum from the low ones. And the principal one that we have been seeing is yttrium, which also have an interesting market along with the people that we are talking with. So these are going to be the rare earths that we are trying to go.
Yeah, but I think like this is like interesting, like just before you add the ammonia oxalate, what you know, like what the rare earth is bonded to? I don't know if it's
You mean if it is in ionic form or is it present in a complex
yeah,
or something?
yeah, I think something like that.
Yes. Well, we think because actually the way we are measuring it is by ICP, and we think that it's an ionic form, but we are not sure about it because we have not made such a extensive or accurate characterization of, of, of the species. We just are measuring in the bulk of an ion.
Yeah, thanks. Is there any other questions on site? If not, I would like to, oh, Christy has a question. Yeah, Christy, do you wanna unmute yourself?
Hi. Yes, thanks, Edson. It was very interesting. I just have a question. You mentioned that one of your objectives would be to do a life cycle assessment. Would you look at only the water and the carbon footprint, or probably the waste as well? Well, that's the first part. And then also, would you then later compare this to these environmental aspects or impacts of this resource recovery system to like traditional mining and of these specific raw materials, or do you have an estimate of the comparison already, or not yet? I don't know if that
We
makes
are still working on it, but what I can show you, what is really important, I just mentioned it very quickly when I was
Sorry,
showing
I think the sound on my side wasn't also not very great, so maybe I missed a few things.
Yes, one of the things that is very important for the impact assessment is, yes, we are going to use chemicals, we are going to transport them, we are going to recover water and reduce the footprint. But one thing that it was a surprise and something positive for us is that we can create credits for capturing CO2. So at the end of the day, we managed to precipitate in the form of carbonates, and also, such as we have an scroll of sodium hydroxide that is capturing the emission of CO2, those byproducts or side effluents that are seen as a waste, they could be introduced into a process of refilling the old galleries in the facility, in the mining facility, and sequestrate the carbon. This will create also a positive emission in the point of view of we are withdrawing CO2 from the atmosphere if we manage to exactly and accurately define the impact or the key performance indicator of the process. But what we have seen yet now is that yes, we have carbon in the content of the scrubber blowdown, total organic carbon. So at the end of the day, it's something that would be introduced either by introducing in the crystallizer, because we have some remaining sulfide that is going to be. So this scrubber, the original the original purpose was to avoid emission of such an acid gas, the hydrogen sulfide. But CO2 is also an acid gas. So at the end of the day, what we are realizing is that we are acquiring both at the same time. And this is something good that we have of sodium carbonate and sodium sulfide that could be introduced either in the crystallizer or in the physicochemical treatment tree by an adjustment of the redox potential in order to transform the sulfide in state. So these kind of things will help us then to this CO2 that comes from secondary sources, this interrelationship with other sectors, such as the glycerol that could came from the production of biodiesel, could be seen as a sequestration, effective sequestration of carbon. So this is something that we are currently working. So besides the classical LCA analysis of seeing exactly the operative condition and the system, to introduce a kind of generation of credits on the process that would reduce, I don't know, I wouldn't say eliminate or make positive the whole process because we don't know yet, but it is a chance.
Okay. No, thank you very much. It's really good.
All right, I think we're out of time. First, thank you very much, Edson. I really like the presentation. It's a very cool project. I would say everyone that wants to contact Edson, I think he'll be more than happy to get in contact or open to collaborations. Just reach out to him either on LinkedIn or email. Thank you very much, Edson.
Thank you very much for the invitation, and I'll be happy to be in contact later.
Yeah, thanks. I think now you're more you can go to sleep because it's been almost 2 a.m. there. And next week you have Janine Herzig from SEEK International talking about contests and gaps in the intersection of water, tailings, and other emissions. So hope to see you out there, and thank you. See ya.
Thank you very
Thanks,
much.
Edson. Bye-bye.